What is up, everybody? We are back. Let's change this. 5. Learning about TPUs. Bang. Okay. Alright, no introduction needed. We are back to how to scale your model. As a reminder, we're doing all this as part of, I'm not sure if I have it anymore, but long story short, the head, oh, here it is. So Vlad Feinberg, head of pre-training for Google Gemini, submitted a blog post, how to land a job at a frontier lab. Posted this May 10th, so we're a little behind, but basically he says at the end, long story short, go through all the JAX tutorials, do every exercise in this book, how to scale your model, do some other stuff, say put your money where my mouth is, record yourself in the JAX scaling book exercises, and have a chatbot convert those results to LaTeX and send it to me, and do some other stuff. So we are doing all the problems in this scaling book here. We read the intro, we did part 1, intro to rooflines, and now it is all about TPUs. So I read this already offline, I guess. But all that means is that we can jump straight into the problems. So let's see, maybe I should try to record this again. Try to record my my paper instead of the instead of my face. Let's see, is that decent? Well, it'll work for now. Alright. Let's get a pen. Done. Alright, so we're on chapter 2, question 2.1. Pause this video. Alright, say you want to sample from a 200 billion parameter model in the BF16 that's split across a 32 TPU V4P. How long would it take to load all the parameters from HBM into the systolic array? It should be a simple lookup, right? What is this? So we don't need to interconnect figures. We just need the HBM bandwidth. We don't care about capacity. We just care about bandwidth, right? I hope we don't have to calculate how many bytes are in a 200 billion parameter model. So you have 32 TPUs. We might actually have to do that, unfortunately. Okay. We have 32 TPUs, they're V4P, so we get, let's just write this down first, TPU V4P, say HBM capacity per chip equals 32 gigabytes. Oh shoot, wrote that wrong. Gigabytes, and then TPU V4P HBM bandwidth per chip equals 1.2 E12 bytes per second. So what do we want to know? We want to know how many bytes in a 200 billion parameter BF16 model so if we have 32 TPU V4P, does that mean we have 32 chips? Okay, so let's just assume that for now. With 32 TPU V4P, we have 32 squared gigabytes HBM capacity, which equals, let me see if I can write this better. What is 32 squared? Let's look it up. 32 squared. 1024, which equals 1024 gigabytes HBM capacity. Cool. Alright. Let's move the camera down a little bit just in case. Next, back to this. Let's make this a little bigger too, actually, so y'all can see a little easier. Next, so does that mean that 200 billion parameters BF16, so 200 billion times the amount of bytes it's in BF16, right? It's 2 bytes per BF16. I think that's what it was. So total bytes in model equals 200 B times bytes in BF16, which equals 200 billion. Let's just make sure before I write this down in pen. BF16. Let's see, where was the matrix multiplication? Because they wrote it down here. Oh no. Oh yeah, but that's per. So it's 2 per parameter because this is a matrix of BF16s. So see, they explicitly say somewhere about BF16 being 2 bytes. Yeah, 2 times n equals 2n bytes. And write 2 bytes back into HBM. Right, see anywhere else? We could also just look it up. How many bytes in BF16? 2 bytes. Yeah. Okay. So it should be 2. Sorry, I'm getting a little distracted. Okay, let's go back. All About TPUs. Let's go back to the bottom. Word problems. Okay, 200 billion times 2, which equals 400 billion bytes. So what does this mean for HBM capacity? Because obviously that's not enough bytes. Um, 400 billion bytes to gigabytes. Let's just type that in and see what happens. It's 400 gigabytes. Oh, what the heck? Okay, never mind, I was wrong. Which equals 400 gigabytes. So we have capacity in our HBM. Now to load into systolic array at 1.2 E12 bytes per second, it will take, okay, so bytes per second times seconds equals bytes. Let's actually write that. Bytes equals bytes per second times seconds, which gets rearranged to bytes divided by bytes per second. Now I should have written that as a slash instead, but whatever. Let's try to do this. You can see it a little better. Second equals seconds. Okay. So that's an easy plug and play. So bytes equals 400. Actually, let's just say 4.00. What is that? Times e to the what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it should be 4 to the 11, but let's just be 100% sure because I'm writing in pen. 400 billion to scientific notation. It's 4 times 10 to the 8. So 4.0 E8 divided by what is it, 1.2? 1.2 E12 equals, let's do, what is it called? Desmos. Desmos Scientific. 4 times 10 to the 8. 400 billion looks right. Right, wait, that looks like 400 million. Yeah, that's not right. Should be then to the 12. 400 billion. 400 billion to scientific. Whoops. 4 times 10 is 11. I'm gonna have to fix that when the LaTeX scanner sees that probably. Anyway, okay, what now? So 11 divided by 1.2 times 10 to the 12. 0.3. 0.33 seconds. Man, I hope that is right. Time to find out. Let's go your model. Okay, let's check that we read this right. Okay, 200 billion parameter model into BF16, and BF16 is split across 32 TPU VP4. Hold on. So it's 1.2 E12 bytes per second. Is that per chip? Or is it one? Is it one HBM for all 32? I have to reread that. No, it's between one tensor core and associated HBM. I bet this number is per chip. Oh yeah, HBM bandwidth per chip. Bruh. So does that mean that I have to multiply it by 32? Bytes per second per chip. Times number of chips. So I'm gonna have to rewrite that later, obviously, before I convert to LaTeX, but now it should be right. So if I'm gonna have to rewrite this anyway, let's just do this. Times 32 chips equals this should be the denominator, by the way. Let's do that. Okay. So let's do bang times 32 equals 0.104 seconds. That seems more accurate. Although still kind of long. Alright, please be right, please be right, please be right. Oh, brother. E9? Why wouldn't it be... I want to be E11. Did I do something wrong? Oh, 400 E9. Okay, yeah. 12.5 E9 bytes per chip. Okay, so I did it the other way. Each with the HBM bandwidth. So the load takes around 10 milliseconds. That's what that is, right? It's pretty cool because it's a reasonable lower bound of latency sampling from 12. Accepts load all parameters from HBM, so it cannot take less than 10 milliseconds. In practice, at small batch sizes, this is close to being achievable. Okay, so we got it. Right? Milliseconds to seconds. Oh, 10 milliseconds, yeah. So 10 milliseconds. Let's go, baby! Okay, so we got it. We got the answer. It has been 20 minutes, so I need to take a quick break. Then we will return back in about 5 minutes. So catch y'all then. Alright, we're back, everybody. Question 2, right? Yes, question 2.2. Let's get right back into it. Alright. TPU details. Consider a full TPU V5E pod. How many total CPU hosts are there? How many TPU tensor cores? What is the total flops per second for the whole pod? What is the total HBM? Do the same exercise for the VP pod. Okay. So right off the bat, I'm assuming that it's a 4.4 by 4 array, right? Isn't every single pod 4 by 4 by 4? Oh, that'd be more than 16 then. Right? The maximum pod size. Huh. So this is a super pod. I don't know if it's the same thing as a regular pod. Let's see, is there any more information up here? No, these are just the basics. TPU networking is what we really want. Interchip interface networking. Connects the 4 nearest neighbors, but still the edges is what matters. I think it is a superpod that we're looking for, though, right? Is there any information in here? Oh, pod size. Oh my gosh. Okay, so it's right here. All right. So what they ask for: a V5P and a V5E, right? Question 2, V5E. Let's do all the V5E first, and then let's do all the V5P. So TPU V5E. Pod size equals V5E. It's 16 by 16. Okay, 16 by 16. How many total CPU hosts are there? There should be 1, right? And there should be 16 times 16 tensor cores, right? So I need to confirm that there's only 1 CPU per pod. Host size refers to the topology of TPUs connected to a single host. V5E has a single CPU host connected to 8 TPUs in a 4x2 topology. 4x2 topology. That doesn't tell us anything. Oh, host size. Oh. Okay. So there's 8 TPUs. So that means one TPU has like 0.16 CPUs, right? Which is they're sharing. A full pod. How many CPU hosts are there? Less than 1 technically. Right? How many TPU tensor cores? That one should be easy. So what's the difference between a TPU and a TPU tensor core? Let's start all over again. Okay, so this is a tensor core. Didn't they say that each TPU generally has 2 tensor cores? No. TPU chip typically consists of 2 TPU cores which share memory. I thought it was one large accelerator. That's true for V5. V5 has 2 tensor cores per TPU. Let's just like write all the information that we know down first, and then we can deduct from that. Okay, so we know that. Okay, this is what we really want to know too. Chips are arranged in sets of 4 on a tray, connected to a CPU host via PCIe network. This is the format most readers will be familiar with. 4 chips, 8 cores, though usually treated as 4 logical megacores, exposed through collab or a single TPU virtual machine. For inference chips like the TPU V5E, we have 2 trays per host instead of 1. This is very important. We have 2 trays per host instead of 1, but also 1 core per chip. And those 8 chips equals 8 cores. I need to think about that for a second, to be honest. Oh, okay. Only for V5P. Okay, so this is going to be a key difference here that we're going to have to remember for the distinction between V5E and V5P. So it says for inference chips, so the V5E, we have 2 trays per host instead of 1, but also 1 core per chip. I wonder if this is going to balance out, but anyway. For V5E, we have 2 trays per host instead of 1, but also only 1 core per chip. Okay. So let's just draw a diagram. So V5E diagram. Let's do, so we have 2 trays, right? So 2 trays. So let's write host. We've got a tray on the right. We've got a tray on the left. Let's make this big square. This big square. We got, do we have 4 chips per tray? But also 1 core per chip. How many chips do we have per tray? Does it say? Host size? 4 by 2. Okay, so I would assume the 4 means 4 chips in a tray. Bang, bang, chip, 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 chip. And then on this one, we're going to leave 1 of the chips not labeled as a chip so we can break it down. So it's 1, but also 1 core per chip. So I'm just going to write an annotation here. Only 1 core per chip. Okay, so total chips per CPU is 8. And then total cores per CPU is also 8. And then we know that does pod size refer to cores, or does that refer to chips? So the next thing I want is total. No, I want. Yeah, what does that 16 by 16 mean? 16 by 16. Host size refers to the topology of TPUs connected to a single host. There's 8 TPUs and a 4x2 topology. Okay, yeah, so a single host is connected to 4 TPUs. Okay, so each chip. So let's just relabel these. Let's say TPUs. Let's say this is tensor cores. Okay. So we can just do simple division now. So we want to know, well, also we want to know, does this, oh, it doesn't matter if it's cores or chips because it's the same math. So I'm going to cheat a little bit. So 16 squared equals, I'm just going to write, oh, sorry, y'all can't see. I'm just going to write that it's cores. No, it's chips. It's got to be chips. All right, might as well just verify it really quick. So where do they first talk about pods? TPU pods. Okay, yeah, so it's chips. So 16 by 2 equals, oh my god, how much, what is that? 16 squared, 256, I should probably have that memorized, huh? 256 chips, let's just do this, 256 chips divided by, we have 8 chips per CPU equals, divided by 8, 32, whoa, what the hell, 32 CPUs? Okay, that does not sound right. So 32 CPUs per pod. You know what? Actually, that does not sound that weird. Because you have to do this twice per 16 thing here. So you got boom, boom, you got 2 CPUs. You got 2 CPUs going down 16 rows, that's 32. Yeah, that's right. Okay. What's next? So we're going to need to move to the next page. So question 2.2 continued. To continued. All right, let's get y'all a little closer here. Next thing. Oh shit. Okay, good. I didn't see anything. So we got total CPU hosts. How many TPU tensor cores? Since, oops, each chip has 1 core, total number of chips, which is 256, right? 256 equals total number of cores. Let's just do that down here. Which equals 256 tensor cores. Okay. What is the total flops per second for the whole pod? So what we want is, so let's write total flops per second equals flops per second per core times 256 cores. Let's go back here. Okay, per chip. Per chip. Okay, total flops per second per chip. Assuming we're doing BF16. Actually, let's write that. Assuming BF16, and let's say equals was total flops per second V5E 1.97E. Oh wait, okay, yeah, 1.97 E14 times 256, which equals, get science calculator up here, 1.97 times 10 to the 14 times 256 is equals 5.04 times 10 to the 16. Oh, I should have said E16, but whatever. Alright. So that's how many flops per second we got for the full pod. Let's label that. Flops per second. The whole pod. Alright, cool. Now, next. What is the total HBM bandwidth, I'm guessing they mean? Or the total size? Don't know exactly what they mean there. Let's see. Do the same exercise for TPU V5P. Okay, what is the total HBM capacity? Probably is what they mean, alright? Or bandwidth. I'm just going to do both just to be safe. Total HBM capacity equals HBM capacity per chip times number of chips, 256, which equals, oh, whoops, I forgot to, what is it? 16 gigabytes times 256, 16 to the third, it's 4096, which equals 4096 gigabytes. And no, I'm not changing that to terabytes. It's probably 4.096, right? Alright, and then total HBM bandwidth. Total HBM bandwidth equals HBM bandwidth per chip times the number of chips, yeah, bandwidth, yeah, times 256, which equals E5E, HBM bandwidth per chip, 8.2 2E11 times 256, which equals 8.2 times 10 to the 11 times 256. 2.1 E14. Alright, that should be everything. Let's see how we did. Just make sure that, oh, I need to do the same exercise for TPU V5P pod. Alright, let's do this again. Question 2.2 continued. Okay, so what I'm going to do here is I'm going to take a quick break, and we will be back in a second to continue doing this for the TPU V5P pod. Alright, we're back. Time to repeat this whole analysis for the TPU V5P. So let's first write that down. TPU V5P. Oops. Okay. Let's just write down differences from V5E. One is so literally every number is different. First of all. Second of all, there should be 2 cores per TPU. And all specs. Okay. So I'm guessing this host size means that there's 2 by 2 by 1. So there's 1 CPU per 2 by 2. So what did 4 by 2 mean again? So 4 chips and 2 trays. So what does 2 by 2 by 1 mean? So let's say there's 2 chips and 2 trays. So 2 chips per tray and 2 trays per every 1 what? What does the third thing mean? I mean, obviously it's like this is 3-dimensional, this is 3, this is 2, this is 2. So I could probably think of it in the 2D versus 3D way. So it's like for a 16 by 16 array pod, you have this stacked 8 times, right? It's stacked 8 times this way, and you have it stacked 4 times this way. And yeah. So for the V5P, you get it stacked like 16 chips this way. You have 20 chips this way and 28 chips up and down. So honestly, my assumption is just that there's 2 trays and 2 chips per tray. I'm just gonna write that down. So I think I'll just say that host size implies the following diagram. Say CPU, still talking to 2 trays. Ooh, wait, is that true? Because I remember them saying earlier that that was a unique thing about the V5E. We have 2 trays per host. In that case, I think we might have done this wrong. So we have 2 trays per host. Instead of 1. Okay, so we have 2 trays. But then this is a 2 by 2 formation, right? We want a 4 by 2. I think we might have done this wrong. Four by 2. Is that the layout of the... I wonder if that's the layout of the, like, tray. I'm kind of thinking it is now. So, did they say specifically what this diagram is like for? So sets a 4 on a tray connected to a CPU via host via PCIe. 4 chips, 8 cores, 4 logic cores. So it's a collaborative single CPU VM for inference chips like TPU. We have 2 trays per host instead of 1. Also only 1 core per chip. There's 8 chips. Eight chips equal 8 cores. But it's not saying 8 chips per CPU, is it? So I have a feeling that this is wrong, but let's continue with the V5E for now, just in case. So get rid of that. And I'm going to assume it's a 2 by 2 as in chip. And I'm going to leave this open to say 2 cores. Chip. And do that. Annotate 2 cores per chip. This might be the first problem that I get wrong, just because it's difficult to know exactly what host size means. Some of these numbers. Well, let's keep going. Assuming that that's right. Consider a full TPU V5E pod. How many CPU hosts are there? Okay, yeah. So let's say we have 4 chips per CPU. Pod size of 20 by, what was it, 20 something, 16 by 28? Yeah, 16 by 20, 20 by 16 by 28 equals 16 by 20 by 28 equals 8,960 chips, which equals So divided by, let's get rid of this. Answer divided by 4. that seems wrong, but let's see. 2,240 CPUs. Yeah, I just don't know anymore. Well, let's just keep doing the arithmetic, see where it goes, and check the answer. Okay, how many TPU tensor cores? 8,960 times 2 equals, what is that, 1792, right? 8,960 times 2, 17,920 tensor cores, and then total flops per second of the whole pod. So flops per second per chip times number of chips. So total flops per second equals flops per second per chip times chips, which equals V5P 4.59 E14 times 8,960. Gosh, that's a lot. Let's move this down so y'all can really see. I'm writing down here. At least kind of see. All right. Oh yeah, we need to do this math now. So 4.59 times 10 to the 14 times 8,960. Sure, it's this. Equals 4.11 E18. Wow, that is a lot. Flops per second. Okay, question 2.2 continued. Sure. What's next? What is the total HBM? Total HBM capacity equals HBM capacity per chip times chips, which equals V5P. HBM capacity per chip is 96 gigabytes times 8,096, right? Oh shoot! Oops. It's 8,960. Times 8,960. Let's do that. 6 times 8,960. All right. Sure. Equals 8. Let's just do 0.6 E. 1, 2, 3, 4, 5. E5. Let's just divide this by 10 to the 5 to make sure that's right. Oh, whoops. Divided by 10 to the 5. Cool. That 5 gigabytes. Alright. Total HBM bandwidth equals HBM bandwidth per chip times chips, which equals 2.8 E12 times 8,960, which equals 2.8 times 10 to the 12. That's multiplied by 8,960 equals 2.51 E16. Is that everything? Alright, so I think that, oh shit. Alright, that should work. I think these questions about the CPUs, the CPU configurations, I probably have wrong. I mean, this kind of seems right for the CPU, or for the V5P, just considering that was kind of what the diagram above looked like. But now I'm starting to think that this diagram of the 4 chips here and the 4 chips here and the 2x2 configuration is wrong. It's probably a 4x2 configuration. But I'm not going to redo the work quite yet. If it's wrong, I can just redo the rewrite the answer before I scan to LaTeX. So let's check the answer. For TPU V5E, each pod is 16 by 16. Oh wait, also let's go back here and look at V5E. I'll hold the camera actually by hand just so you can read it better. Alright. Pod size is 16 by 16, and each host is a 4x2 slice. So we have 16 times 16 divided by 8 equals 32 hosts. Oh, okay, so I got that right. 32 CPUs. For TPU V5E, each TPU has only 1 core, so you have 256 tensor cores. I think man, this cable's annoying, but whatever. Let's just put this on top of that cable. Okay, tensor cores. Since each chip has 1 core, total number of chips 256 equals total number of cores. 256 tensor cores, because that's right. Total flops per second is 16 by 16 times 2 e to the 14. What? Total Did I get flops per second wrong? 2e14. V5e. What? 1.97 E14. Oh, did they round to? Oh, yeah, they rounded. It was 5.1 E16. So, basically the same answer. For a full TPU V5P pod. Okay, so on to V5P. Wait, did we? Okay, each chip has 16 gigabytes of HBM, so that's 4 terabytes of memory. Bang. Yeah, so we got 4,000, so 4.1 terabytes really. So they didn't even want bandwidth, they just wanted capacity. Anyway, so on to V5P. See if I can one-handed flip the page. done. All right, let's see what we got here. We got right. We have 16 by 20 by 28 chips, and each host is 2.2 by 2 by 1. So we have 2,240 hosts. I got that wrong. Oh, no, I got that right. Oh, I'm surprised that I got that right. Okay. For TPU V5P, each TPU has 2 tensor cores. So we have 17,920 cores. Bang, got that right. Total flops per second is 8,960 times that number, which is 4.1 E18MB float. 4.1 E18. And HBM. 96 gigabytes HBM, so we should have 860 terabytes. Yep, that's what I got. 860 terabytes, which is the same as 860,000 gigabytes. Cool. All right, let's put this bad boy back. Pedestal. And we're going to take another quick break, and then we'll come back and we'll solve question 3. See y'all then.